Introduction to matter. Definition. Matter is defined as anything that occupies space, has mass, and can be perceived by the senses. Means it will have a particular space, it will have its own mass, and it can be also felt by our senses. That if you're touching it, you'll know that the matter is present over there. Composition of matter. Matter in any state is composed of small particles, molecules, atoms, or ions. So all matter will have some smaller particles inside, which could be molecules, atoms, ions. Then characteristics. An atom is the smallest particle of an element which can take part in a reaction and is considered the basic unit. Example, OH and Cl are atoms. So atom is the smallest possible particle of the element and it can take part in all the reactions also. Molecules. A molecule is the smallest particle of a substance which can normally exist separately and retain the characteristics of the substance. So whatever substance is there, still it will reflect the properties too, and it is also again the smallest particle and it exists separately unlike the atoms. Ions. An ion or an atom is any atom or a group of atoms which has a resultant charge due to the loss or gain of electrons. So if there are more electrons, the power will change, and if it's less also, it will be affected. That is known as an ion. Example, O2, H1, Cl1, and ions. Characteristics of matter, volume. Now this part is very important, just mark it. All of these are the definitions. Volume. Matter occupies space, which is known as its volume. Means how much space it is going to take, that we can call as volume. Mass. The quantity of matter represents the mass. Means how much matter is present in that one particular object. That is known as my mass. Weight. The gravitational pull on matter represents its weight. Means how much force is pulling it downwards, which is of the gravity. Perceiving of matter. Matter can be perceived by touch, light, sight and smell, etc. So we can see it by touch, sight and smell. Examples of matter: living, plants and animals; non-living, air and water. Now I'll give you all 2 minutes. Just go through the states of matter, which are solids, liquids, gases, and then we'll discuss it. Yeah, first thing, space. Solids occupy space, liquids also occupy space, and gases also occupy space. So this point is common for all three of them. Then mass. Solids, liquid, and gases, all of them have mass. Next one, volume. Have a definite volume, have a definite volume, and have no definite volume, because gases will be flowing randomly in everywhere. It's not that it has to be at a fixed place only. Volume, then shape. Have a definite shape, have no definite shape, and have no definite shape. Solid is always fixed, and whereas for liquids and gases, it will take the shape of the container where it's present. Suppose liquid I'm keeping in a, suppose there's a utensil in the kitchen. There's a utensil in the kitchen, so it will take the shape of that. Otherwise, if it's a bottle, accordingly, it will take the shape. And similarly for gases also, it will take the shape. Density, have a high density, have a less density, and have the least density. Compressibility, it cannot be compressed, means I cannot push it into a smaller space. It will remain fixed in the same area that it was taken. Slightly compressible, so liquids I can fit into a smaller utensil or some other thing. Highly compressible, so gases can fit in anywhere, so they can even be taken as smaller spaces. Free surfaces, any number of free surfaces, one upper free surface and no free surface. That is your surfaces of the solids. So it will be more in solids, liquids only one, and in gases not there. Diffusion, cannot diffuse. Diffuse refers to spreading. Shows diffusion, which is liquids. So it will move according to the article where it is kept and very easily diffuses. So gas will easily spread all around. Yeah. Then the next page. Kinetic molecular theory of matter, main postulates. Composition of matter, particles. Matter in any state, that is solid, liquid, or gas, is composed of smaller particles, molecules, atoms, and ions. This we've already read on the previous page. Interparticle space. The particles are arranged in such a way that they have the spaces existing between them, that is intermolecular space. The molecules should not be stuck to each other. There will be some certain space in between, so they can even move a little. Interparticle attraction. All the particles attract each other with a force which is maximum if the particles are close to each other, Means however close, that means maximum. And if it is spread apart, that will become the minimum. That is, it will decrease with an increase in the distance and vice versa. So it depends on the distance of the molecules, how far they are kept. Energy possessed by the particles of matter, kinetic energy. Since the particles are in a continuous motion, they possess an energy which is called kinetic energy. Application of heat increases the kinetic energy of particles, which then move more randomly. So if there is more kinetic energy, the particles will also start flowing around more. Kinetic theory of matter, solids, interparticle space between the particles is minimal. So there is least space in between the molecules of a solid. Interparticle attraction between the particles is maximum, means they will attract each other. Kinetic energy of molecules in a solid is the least. They will not be able to move freely as in the cases of liquid and gases. In liquids, the interparticle space between the particles is slightly more than solids. Interparticle attraction between the particles is less as compared to solids. And the kinetic energy of the molecules in the liquid is large. So they can flow according to the liquid, how much of a quantity, and they'll use their space and start moving. Gases, interparticle space between the particles is comparatively very large. Interparticle attraction between them is negligible, and kinetic energy is very large. The next page. Yeah, now go through this page. I'll give you 2 minutes. This is again the same thing which we have done, but in a shorter form, like in a distinguished form. And mark this table. You'll need to learn it also. I'll wait for 2 minutes and then we continue. Yeah, Law of Conservation of Mass. Lavoisier, 1789, formulated the law on the results of experimental evidence. So first he did an experiment, and out of that he proved his law that after doing the experiment, this is the final conclusion, and how he's done the experiment.
Miss, you missed 2 pages.
You missed 2 pages.
Oh, no,
Yes.
sorry. Akshara, can you start reading? So I'll
Three
find
says.
it. Okay, fine. Found it. Yeah. Sorry. Matter exists in three states: solids, liquids, and gases. Matter may change from one state to another state on the change of temperature, pressure. This change is termed as a change of state of matter. So, because of my outside factors, the change will happen in the state. So it will become from, suppose, solid to liquid or liquid to gas. And just mark this. This is a definition. Then interconversion of matter involves the change of state of matter from one state to another state and back to its original state. This change is brought by the change in temperature and pressure. For example, ice. So it will first make it into ice, and you can even melt it and get back the water. The terms melting, conversion of a solid into liquid on heating. So when I heat the solid, it will turn into liquid, that is ice to water. Vaporization, conversion of a liquid into the vapor on heating. Example, water to water vapor. Liquefaction or condensation, conversion of the vapor into a liquid. Example, water vapor to water. Solidification or freezing, conversion of a liquid into a solid. Example, water to ice. So when there's a liquid and it becomes solid, that is an example of water to ice, which is solidified. Sublimation, conversion of a solid directly into the gas form, and on cooling, directly back to the solid without changing into liquid. Example, naphthalene sublimes at the room temperature. So liquid state will not come anywhere in between. Directly solid to gas and even back to solid. Everyone clear with this page? Gurpreet, getting it?
Yes.
The next one. Change of state of matter on basis of kinetic theory. Interconversion of matter on basis of kinetic theory. On heating solids, the temperature rises. So when I'm giving heat, obviously the temperature will increase. Particles gain energy. Light and the heat energy supplied to the solid is absorbed by the molecules, and it is stored as a potential energy. So the heat energy is taken in, and I keep it stored as a potential energy, so I can use it in the future if needed. Interparticle space increases. The stored potential energy increases the space. So as there is more energy, even the molecules will be a little more spread out. Interparticle attraction decreases. The force of attraction between the particles decreases. So there will be less attraction between the particles. At the melting point, the particles become free. The molecules become free and the solid will change into a liquid. Example, if there is ice and I'm heating it, directly it will go to the water form. That's the liquid form. And vaporization. On heating the liquids, the temperature will rise. Particles gain energy. The heat energy supplied to the liquid is absorbed by the molecules and again stored as a potential energy for future use. Interparticle space increases. The stored potential energy increases the space. Interparticle attraction decreases. The force of attraction decreases to almost negligible, so it's hardly there, only minimum. At the boiling point, the particles become free. Molecules become completely free and they escape as a gas. So now from liquid it has gone to gas and it is going away as if it's water vapor. Then liquefaction. On cooling the gases, the temperature falls. Particles will lose energy. On cooling the gas, the potential energy in the molecules is released as heat. So now this is the reverse. First I was taking heat, converting into potential and storing. Now I'm giving out the potential energy in the form of heat. Interparticle space decreases greatly. The released potential energy decreases the space. So if the potential energy is given out, the molecules will come closer. Then interparticle attraction increases. The force of attraction between particles increase because they will start attracting. There's no energy in between to keep them apart. At the liquefaction point, the particles slow down. Molecules are not in a position to be free, and the gaseous state will change into the liquid state. So they cannot become free. This is the opposite of the above one. And the gaseous state will become liquid. Then solidification. On cooling the liquids, the temperature falls. Particles lose their energy. On cooling the liquid, potential energy in the molecules, it is released as heat energy. So again, potential to heat. Interparticle space will decrease. The released potential energy decreases the space. Interparticle attraction increases. The force of attraction between the particles will increase. And at the solidification point, the particles slow down. Molecules are not in a position to be free, and the liquid will again change back to the solid state. Then the next one, sublimation. On heating a sublimable solid, that is ammonium chloride, interparticle attraction is low. The sublimable solids have a very low force of attraction between their particles. So sublimable refers to the ones which will go from solid to gaseous directly. Interparticle attraction is overcome. On heating a sublimable solid, the interparticle attraction is overcome. The molecules break free and escape from the surface of the solid directly into the vapor. So the molecules are given out directly as gaseous. There will not be any liquid state in between. Yeah, and the last part.
Miss,
Yes, Akshay.
Miss, can you explain that melting and vaporization ones?
Yeah, we'll do it again. Yeah, Akshara, you read the points once, then I'll go on explaining mine.
Particles gain energy. Heat energy supplied to the solid is absorbed by the molecules and stored as potential
So
energy.
I'm heating the substance on a, let's say on a gas, imaginary. So I'm keeping it on the gas, the heat energy is given, and I'm storing it as a potential energy inside the solid. Then continue.
Inter- interparticle space increases. Stored potential energy increases the space.
So there is more potential energy in between, so my molecules will move a little apart. That's where the space will increase.
Interparticle attraction decreases. Force of attraction between particles
So
decreases.
they will not be very close. That's where the force of attraction will also start to weaken.
At melting point, particles become free, molecules become free, and the solid changes to liquid.
So that ice cube is finally turning into water. So the particles are free now to go in the form of liquid. Yeah, and next one.
Vaporization. Particles gain energy. Heat energy supplied to the liquid is absorbed by the molecules and stored as potential energy.
So same thing. Again, I'm heating it and it is trapped as a potential energy.
Interparticle space increases. Stored potential energy increases the space.
Again, potential energy will come between my molecules and it will increase the space.
Interparticle attraction decreases. Force of attraction decreases to almost negligible.
So it's hardly there, as if it is not present, just minimum amount.
At boiling point, particles become free, molecules become completely free and escape as gas.
The molecules will go out in the form of gas because liquid is changing into gas. Clear now, Akshay?
Thank,
Miss,
thank you, Miss.
Yes, Naisha?
Miss, I was asking that when the like when a solid is changed to a liquid or liquid is changed to a gas on heating, the potential energy changes into kinetic energy at that point only, no?
Yeah, at that point. And sometimes it could be even heat energy when I have to give out the energy.
Okay.
Yeah. Then we move to the next one, the law of conservation.
Thank you, ma'am.
But, law of conservation, Lavoisier formulated the law on the results of experimental evidence. So he has conducted an experiment, then he has proved the procedure, and finally he's given his conclusions. All that we have to learn. The statement: whenever a chemical change takes place, the total mass of the reacting substance is exactly equal to the total mass of the product, provided the masses are measured under similar conditions. They should be kept in a similar balance machine so that we can measure it correctly. And the reactants and the products have to be equal. That is the main point. It can also be put forth as matter is neither created nor destroyed during a chemical reaction, but it changes from one form to another. So I'm not making anything new, nor am I destroying the old one, but it is just changing the substance form. So suppose it is solid to liquid, how we learned. So it will change the form, and nothing, no other changes there except that. Explanation: if A and B react to form C and D, so A and B are my reactants, C and D are my products, then according to the law of conservation of mass, the mass of A plus the mass of B is equal to mass of C plus mass of D. Basically, my total mass before the reaction and total mass after the reaction both have to be balanced or equal. Then experimental evidence. Landau used the H-shaped tube, which is given in the diagram above. It looks like an H, as shown above, and introduced a solution of sodium chloride, which is NaCl, and silver nitrate, AgNO3, in the limbs of the tube, which is the thin parts. It's over there. The solutions of BaCl2 and Na2SO4 could also be used in the H-shaped tube in place of NaCl and AgNO3. The two options are there, either the first two or the other pair. The tube was then sealed, so completely packed, and weighed before the experiment. So just taking the weight before. The solutions were mixed with each other by shaking, and a white precipitate of silver chloride was obtained. So after the reaction, I get silver chloride, which comes out as a precipitate. The tube was again weighed after the experiment. So first thing was before the experiment, you have to measure it, then mix them, so there will be a precipitate form, and again I will take the weight. So result: the weight of the H tube plus the reactants is equal to weight of the H tube plus the product. And the reactions are given. Those reactions are very important. It's even a text bag answer for all this page. The limitations of the law. Landau observed the causes for a very slight error in the experiment. So there was a minor error, so that he tried to understand. The chemical energy stored in the reactants is released in the form of heat or light. So there was chemical energy in those reactions. So that is released in the form of heat or light, because they're doing the experiment. So it might give out a small light also with the precipitate. Hence, the mass is converted to energy, and thus mass and energy are to be considered together. This correlates with Dalton's atomic theory that atoms can neither be created nor destroyed, but they change from one form to another. So there is no new atom or destroying the old one. We are just changing the form from one to another. Clear with everyone? Siddhi, Akshara, getting it?
Yes, ma'am.
Okay, now I'll
Yes. Miss, can you just explain the limitation once more?
Yeah, limitation. Okay, we'll repeat it. Landau observed the causes for a very slight error in the experiment. So after doing the experiment, he realized that there is some small problem. So for that, he tried to study it again and find the cause for that. The chemical energy stored in the reactants. So my reactants are NaCl and AgNO3, which has chemical energy. And after my reaction, it is released in the form of heat or light. There could be a heat because of this change in temperature, or there will be light given out. Hence, the mass is converted to energy. So from the mass which I was having before, I'm converting that to energy. And thus, mass and energy are to be considered together. So you have to consider both of them. This correlates with Dalton's atomic theory. So they're comparing it with Dalton's atomic theory. Atoms can neither be created nor destroyed. So we cannot make or destroy it, but change from one form to another. That is by the means of any reaction taking place. Now it's clear, Naishna?
Okay, miss. Yes, miss. Thank you.
Now,